Hi, good morning. This is Trina here to discuss about the basic principle of spectroscopy. And this is the second lecture, and today I will discuss about IR spectroscopy. And in the first lecture, I have told about the basic principle of the spectroscopy, definition of spectroscopy. There are different fields of the application. So how it is the useful, it is very important in different field, in the analytical chemistry, not only that in physics, in the biomedical field. So everywhere the spectroscopy is very important for the analysis. So I hope that you have already joined with my course. So course page is given here. So all the study materials is uploaded in this code. So first you need to join with the code, then you can access all the study materials. And not only that, different types of problems and the different types of questions and solved problems. And if you have any doubt, you can communicate with me either through my mobile number or through my email ID. So both are given in my personal information. So the course chemistry, the subject code is CH101 for odd semester and the CH201 for even semester. This course is for undergraduate BTech students. And the streams are CSE, IT, Civil Mechanical for even semester, Electrical ECBME for odd semester. Credits are 3, contact hours 35. Weekly I will take 3 lectures. So the prerequisite knowledge required 12 standard to understand the concept of chemistry. So the course objective, so students will learn the several concepts of chemistry. And in the outcome, so student will be able to learn different concepts, and in the light of spectroscopy, I can tell that students will gather the knowledge of different spectroscopic techniques, and they will be able to determine the structure of different molecules. Here, the entire lecture plans are given so that you can understand that which topics will be covered in which day. So our module, the spectroscopy, it is the last module, the 5th module. So here you can see the name of the module, that is the spectroscopic techniques in chemistry. This is the spectroscopic techniques in chemistry. So first lecture, already you have learned many things, like you have learned the electromagnetic radiation. So there are different types of electromagnetic radiations: UV, ultraviolet, visible, infrared, microwave, X-rays. So all these things you have learned, and you have seen that their wavelength, their frequency, their energies, etc. And also you have learned the principle of spectroscopy, how it is applied, how there is the interaction between the electromagnetic radiation with the matter. And also you have learned the UV spectroscopy. That means how it works. So how the sample absorb the radiation and how we can get the transmittance and the absorbance value, and we can plot the graph. And from this we can understand that which material exists in the sample. So in my second lecture, that is already highlighted, today I will discuss the infrared spectroscopy, fingerprint region, functional group region. Okay, so let's go in the infrared spectroscopy. So first, you need to remember that what you have learned, that is the electromagnetic spectrum. It is the range of frequencies in spectrum of electromagnetic radiation. So here you can see that there are different types of electromagnetic radiations, like say visible spectrum, ultraviolet spectrum. So you have learned in the last class visible, ultraviolet. There is the gamma rays, X-rays, infrared, microwave, radioactive. So today we will discuss about the infrared electromagnetic radiation. So one example I like to give you, that you know that about the greenhouse effect. About the greenhouse effect, what happens? So the incoming solar radiation can penetrate the atmosphere. You know that in the atmosphere there are different gases like oxygen, carbon dioxide, nitrogen, there methane. So there are lots of gases in the atmosphere. So there is a blanket of atmosphere over the Earth's surface. So what happens basically when the incoming solar radiation comes, so it can easily penetrate the atmosphere. So its frequency is less, that is 0.5 micrometer. But the outgoing radiation, that is the earth radiation. So earth radiation, that is basically infrared radiation. Its frequency ranges from like 4 micrometer to the 20 micrometer. So first the solar radiation comes, then our Earth's surface become hot, it is like a hot ball. Now it radiates back. So the Earth radiation is in the range of infrared. So I told that there are different types of gases like oxygen, nitrogen, CO2, but all the gases cannot absorb this radiation. So which can absorb this radiation and which cannot absorb this radiation? So which materials, which gases are IR active? They can absorb the radiation. The gases which are not IR active, they cannot absorb the radiation. Like say CO2 is IR active, but O2, N2 not IR active, or SO2 also are not IR active. That is why we get the greenhouse gases only 6. There are lots of gases, but only 6 greenhouse gases. What are those? Those are CO2, CFC, H2O, O3, N2O, so CH4. They are the greenhouse gases. But O2, N2, SO2, NO2, they are not greenhouse gases. Why not? Because they are not IR active. They are IR inactive. So how we can understand that which is IR active and which is IR inactive? I will show you. So basically, we have to consider the dipole moment. Okay, if the dipole moment is 0, then they are IR inactive. If the dipole moment, it has some dipole moment, so the gases are IR active. So it depends on the dipole moment and it depends on the vibration of the molecule. So there are different types of vibration like stretching, bending. So the frequency matches with the molecule, they will absorb the radiation and there will be different changes like the vibration or stretching, bending, etc. So here the infrared spectroscopy is the analysis of infrared light interacting with a molecule. Okay, so the interaction, this is the, I told that spectroscopy basically the interaction of electromagnetic radiation with the molecule. So infrared spectroscopy, it is the analysis of infrared light. So which is in the infrared region. So this light will interact with the molecule. So this can be analyzed in three ways: by measuring absorption, emission, and reflection. So when the light interact with the molecule, so molecule can absorb this light, it can emit the light, or it can reflect it back. So the main use of this technique in an organic and inorganic chemistry, it is used by chemists to determine functional groups in molecules. IR spectroscopy measures the vibrations of atoms, and based on this, it is possible to determine the functional groups. Generally, stronger bonds and light atoms will vibrate at a high stretching frequencies. Okay, so you understood that it is basically shows the vibration of an atom. So now you can see the picture, that is the vibration in CO2 molecule. So basically you can tell that CO2 is also symmetric, like say O2. O2, there is no net dipole moment, that is why O2 is IR inactive. So similarly you can say that carbon basically looks like that carbon, there is oxygen, and another side there is another oxygen. So basically it looks like that its dipole moment is 0. But actually it has different types of bending and stretching. So it may be the asymmetrical stretching or symmetrical stretching. So stretching is of two types, symmetrical and asymmetrical. So here you can see symmetrical and asymmetrical, and bending, the symmetrical or different types. So now I will show you the video, then you can understand the stretching and bending, which one is symmetric, which one is non-symmetric for CO2. Examples of molecular vibration. So here you will see it is the stretching, CO2. Okay, it is the asymmetric stretching. First you saw the symmetric, then asymmetric. Now it is the bending. It is called bending. It is for like H2O, and it is also, you can say, different types. Okay, so in this way you can see that there are different types of stretching and different types of bending. And not only that, I will show you different types of video. Then you can understand the types of IR vibration. So it is the stretching vibration. It is symmetrical. You can see that it occurs. It is a carbon, that is oxygen. So it occurs symmetrically. So this stretching vibrations is called symmetrical. So you observe carefully, you can understand that is symmetrical. Next is anti-symmetrical. So anti-symmetrical, you can see that one is one oxygen going closer to the carbon, another is going far from the carbon. So it is closer, then it is far, then it is closer. So this one is far from the carbon. So it is called anti-symmetrical vibration. That is also stretching. Next is scissoring. So you can see that how it is doing like the scissor. It is scissoring. It is called scissoring. Okay, that is the bending vibration. So basically the carbon dioxide, in the carbon dioxide we get different types of vibration, and when it is the symmetric vibration, its dipole moment is 0. Now it is rocking. Okay, it looks funny, right? It is rocking. Just rock, 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 you do in the park. So like that, it is rocking. But when the asymmetric vibration occurs, then there we get the dipole moment. So it is not the permanent, so we get the temporary dipole moment. And if there is the dipole moment, then it is IR active. So it is called wagging. So it is coming front and then it is going back. So in this way, wagging taking place. So it is coming front and again it is going back. So it is also one type of bending vibration. So next is twisting. So one is coming front, then another is going back. Again, this one is coming front, another is going back. So in this way, different types of vibration take place in the carbon dioxide. Okay, so now I will show you a very funny video that you will laugh at this video. Okay, so it is not working. Then let's study. Later we will see the video. Okay. So you have understood that vibrational mode of CO2, different vibrational mode, symmetric and asymmetric, carbon-oxygen bond stretching and bending. So when it is symmetric, so there is dipole moment is 0. But when it is asymmetric, then there is dipole moment. And as there is the dipole moment, so we can tell that is the IR active. In this case, it can absorb the IR radiation. That means it can interact with the IR radiation. Okay, this is the funny video. So it looks like they are dancing. Okay, it looks like they are dancing. So bond dipole. Here you can see it is the symmetric stage. The second one is the asymmetric stage. The third one is the bending. It is just looks like the CO2 is dancing. So it is very funny to observe. Okay, so I hope that you have understood practically how the CO2 remains. So it is symmetric and asymmetric, you got it. Okay, so come to the theory part, that infrared spectroscopy is one of the most common and widely used spectroscopic technique employed mainly by inorganic and organic chemists due to usefulness of the determining the structures of compound and identifying them. So chemical compounds have different chemical properties due to the presence of different functional groups. Absorbing groups in the infrared region absorb within a certain wavelength region. Okay, within the certain wavelength region. The absorption peaks within this region are usually sharper when compared with absorption peaks from the ultraviolet and visible region. In this way, IR spectroscopy can be very sensitive to determination of functional group within a sample, since different functional group absorbs different particular frequency of IR radiation. Also, each molecule has a characteristic spectrum, often referred to as the fingerprint. A molecule can be identified by comparing its absorption peak to the data bank of spectra. So IR spectroscopy is very useful in the identification and the structure analysis of a variety of substances, including both organic and inorganic compounds. It can also be used for both qualitative and quantitative analysis of complex mixture of similar compounds. Okay, so IR spectroscopy is very much useful. Now, polyatomic molecular vibration. So the bond of a molecule experiences various types of vibration and rotation. So as you have seen for the carbon dioxide. So there are different types of vibration, like say you have seen the wagging, twisting, rocking, scissoring. Okay, so already you have seen with the video that what are those. Next is region of IR. So this is the IR region. The IR region of the electromagnetic spectrum ranges from 2 to 15 micrometer. 2 to 15 micrometer. Okay. Conventionally, the IR region is subdivided into 3 regions: near IR, mid IR, and far IR. Most of the IR used originates from the mid IR region. Okay, so IR deals with the interaction between a molecule and radiation from the electromagnetic region ranging from 4000 to 40 centimeter to the power minus 1. The centimeter inverse is the wave number scale, and it can be also be defined as 1 per wavelength in centimeter. That means centimeter inverse means 1 by centimeter. So that is basically wavelength in the unit of centimeter. A linear wave number is often used due to the direct relationship with both frequency and energy. The frequency of the absorbed radiation causes the molecular vibration frequency for the absorption process. And the near infrared spectroscopy. So what is its range? Near infrared, it is expressed as NIR region, and its region is 750 to 2500 nanometer. This is very weak. Why weak? Because they arise from vibrational overtones and combination bands. Combination bands occur when two molecular vibrations are excited simultaneously. The intensity of overtone bands reduces by 1 order of overtone for each successive overtone. When a molecule is excited from the ground vibrational state to the higher vibrational state, and the vibrational quantum number V is greater than or equal to 2, then an overtone absorption results. So the first overtone results V is equal to 0 to V is equal to 2. Second overtone occurs when V is equal to 0, transition to V is equal to 3. Okay, so transition arising from near IR, that is NIR absorption, are weak. Hence, they are referred to as forbidden transitions. But these transitions are relevant when non-destructive measurements are required, such as a solid sample. Next is the far infrared spectroscopy. So the far infrared region is particularly useful for inorganic studies due to stretching and bending vibration of the bonds between the metal atoms and ligands. The frequencies which these vibrations are observed are usually lower than 650 per centimeter. Pure rotational absorption of gases is observed in the far IR region when there is a permanent dipole moment present. Example include H2O, O3, HCl. So our next is the IR analysis. So IR spectroscopy is a great method for identification of the compounds, especially for identification of functional groups, as I told earlier. Therefore, we can use group frequencies for structural analysis. Group frequencies are vibrations that are associated with certain functional groups. It is possible to identify a functional group. So there are different functional groups like CO, CH. So it can be analyzed through the IR spectroscopy. So let's take one example, that is for formaldehyde. Okay, we take the example for formaldehyde. And formaldehyde has the CO functional group and CH bond. So the value obtained from the following graph compared to those in reference data blank stored for the formaldehyde. A molecule with CO stage has a IR band usually found 1700 per centimeter. That means centimeter inverse, and around 1400 centimeter inverse for CH to bend. Okay, so this information we have. So when we pass through the IR radiation through any sample, any molecule, so if it matches with the radiation, then we can conclude that this spectrum is for formaldehyde. Okay, so for like the CO bond, C double bond O and CH bond, we know the specific spectrum. So if it matches with this, so we can say that this bond, this functional group exists in the molecule. So in this way, this is the spectrum of the formaldehyde. It is known. Now say there is a reaction and it is the unknown reaction. Say we are doing some observation. Now IR radiation passed through the sample. If it shows the same spectrum, so we can conclude that in our sample there is the formaldehyde. Okay, you are very clear about this and about the application of the IR radiation. So if I summarize the applications, so what are those? Number one, infrared spectroscopy is a simple and reliable technique widely used in both inorganic and organic chemistry, in research and industry. It is used in quality control, dynamic measurement, and monitoring applications such as a long-term unattended measurement of CO2 concentrations in greenhouses and growth chambers by infrared analysis, gas analysis. Number two, it is also used in forensic analysis in both criminal and civil cases. For example, identifying polymer degradation. Number three, the IR spectroscopy has been successfully used in analysis and identification of pigments in painting and other earth objects. Infrared spectroscopy has also been successfully utilized in the field of semiconductor microelectronics. For example, infrared spectroscopy can be applied to semiconductors like silicon. Okay, so what you have learned today? You have learned lots of things. You are learning the spectroscopy, that is very important techniques in the chemistry, not only in the chemistry, and different fields for the analysis of the chemical or analysis of the different molecules. So here we can identify the which functional group is present in the molecule. So what you have learned, if I summarize, first of all, you have learned that what are the different types of electromagnetic radiation, what are the ranges of the IR radiation, infrared radiation, and in the infrared radiation, that means how it works. Like say, the dipole moment, if any molecule has the dipole moment, then it can absorb the IR radiation or it can interact with the IR radiation, and then only we can say this is IR active. Like you have seen for the CO2, you have seen that different types of bending and stretching takes place, like it is symmetrical, it is asymmetrical. So apparently the CO2 looks like that it is symmetrical, it don't have any dipole moment is zero, but actually the practically there are different types of bending and stretching. So for asymmetric stretching we get the dipole moment for CO2, and as we get the asymmetric structure, as we get the dipole moment, so it is IR active. So it absorbs the radiation around 15 micrometer range. So we can understand that different types of functional group from the IR radiation. So few, that means the different functional group which is IR active, it will show the graph as you have seen for the formaldehyde. So if we know that this bond, this functional group shows this type of peak, then we can matches and we will say that this group is present, like say ketone group present or aldehyde group present, this we can say. So now I am ending my session. I hope you have understood all these things. If you have any doubt, you can communicate with me. So thank you everyone.